Hello. Today I'm going to show you how to get OpenFOAM and run a very simple transient simulation with heat transfer. So first of all, you need to be familiar with Linux. Even if you are going to try to use it on Mac or Windows, basically how they run it is by using a virtual Linux system. And so why not just use Linux anyways, because it's better. Jokes aside, you can use Docker for Mac, and then same with Windows, or you can use the Windows subsystem that's already built into it. So assuming that you do have a Linux distribution, this is the easiest way to get it. I'm assuming 90% of you are going to be on Ubuntu. There's probably a few Fedora and Arch users here, and they should know pretty much already how to get their stuff. So first you have to get a repository. So just use one of these two, and then once you have the repository and you've updated your system, you want to install OpenFOAM there, and then that's how you remove it. So it's pretty simple, pretty easy to get. And then how you actually run it. So here's my bash rc file. So I am editing it. And I think it's in my bash aliases. Yeah, here you go. So it's best practice to do this because you'll probably end up using multiple versions of this. If you haven't already realized, there's an openfoam.org and then an openfoam.com. And in my experience, openfoam.com or the ESI group just has better and more features, and is simpler to use. So the version I'm using is 2206, and so how I would actually initiate that is clear that so you're not confused. There we go, and now I am ready to run OpenFOAM. So the solver that I'm going to be introducing you today, and there are many solvers that are already built into OpenFOAM, but what makes OpenFOAM so great is that it's very easy to make your own for academic purposes or even commercial applications. Alright, here is the solver we'll be using today, and we might not actually be using it quite right, but that's not entirely important for this tutorial. This is typically used for compressible fluids, but with some modification you can use it with incompressible, but there are other solvers which are just more readily built for that. As you can see, the source code is very easy to read. This is the pimple algorithm, which is the transient algorithm, and now we're just correlating it with density and heat transfer. So with that, let's I should probably post some files for everyone to grab, so it's very easy to just jump into following me in this video. So with that, we will start our case. So this is what the layout for an OpenFOAM case looks like. There are 3 folders. The first has your boundary conditions and your initial conditions. And then the constant folder has constants like gravity, thermodynamic properties or thermal physical properties, and your turbulent model. System has systems that will run your actual case, like a control dictionary. And what the control dictionary does is it says what solver you're using, how to run it, when to stop, and then how often you want to write, and other control parameters like your courant number. FV schemes and FV solutions, they stand for finite volume schemes and finite volume solutions. So the schemes are going to look pretty familiar if you've taken any sort of numerical methods class. You have your Gauss linear, Gauss upwind, etc. And for the most part, you can just pull these from a tutorial case that is similar to what you're doing, and they should work pretty well. With the exception of FV solutions, you want to make sure if you're doing the case we're doing today, which is a density-related case, that you don't have the density reference cell in your Pimple algorithm solver, as we're going to specify that on a boundary condition. So the constant filter has gravity, and you can specify gravity in any quantity you want, in the x direction, the y direction, and then finally the z direction. Your thermal physical properties are pretty important, and you want them accurate to what you're doing. So it's best to always just test them. What this is polynomials, and there's lots of other expressions you can enter into your thermodynamic properties, your thermophysical properties. And so if we check this, these all look very close to what we find for water. And you can double check that on Google. Again, I'll probably go over these in a later tutorial, but this is a very basic case setup. For our turbulence model, we're going to stick with laminar. It makes things simple. We don't have to get into a turbulence model just yet. However, you'll find that that's kind of needed depending on your geometry and your Reynolds number. Before we get into the boundary conditions and the initial conditions, let's look at how we first make those boundary conditions. So this is our block mesh, and this is the most basic mesher that comes with OpenFOAM. And what it's doing is making a series of vertices, and then we're taking those vertices and we're making it into a block. So starting from the back left corner, we are making 8 vertices, and that makes a cube. And then I've subdivided it into a few hundred blocks here. These are basically variables, and then a calculation. And you'll notice that the context for OpenFOAM files are very similar to C++, brackets and semicolons. So once your cube is made, you'll take these vertices and you'll make faces with them, and then you'll assign the faces a patch or an empty or a wall. And for this case, our bottom and top are going to be walls, and then our front and back are going to be empty because it's a 2D case. And then our inlet and outlet are going to be patches. And patches are pretty much anything that isn't a wall. And there are a few other I guess, patch types, but those are the very, very basic ones. So here are boundary conditions and our initial conditions. So starting with velocity, or u, our inlet is going to be a fixed value, which means there is just a set value of velocity, and that velocity is 2 millimeters per second in the x direction. So it's a very, very slow flow, almost stagnant. And then the outlet is an inlet-outlet condition, and what that basically does is suppresses reverse flow. Any reverse flow that does come through is assigned this value. And then our bottom top are the no slip condition, and if you know anything about fluid dynamics, it's a very basic boundary condition for water moving on a surface. And our front and back are empty, and that's just for our 2D case. There's nothing going on there, so it's kind of like an infinite channel is what our case setup looks like. Our temperature is pretty much ice water is what we're starting with. So most of these are in SI units, and if you look at these dimensions on OpenFOAM.com or some reference, they'll show you that each position is an SI unit, and so I'm assuming this one right here is Kelvin. So 280 Kelvin. Our inlet is going to be ice water. Same with any reverse flow that we get. Again, front and back are empty, and the top is a insulated boundary condition, so 0 gradient. So no heat is being moved across that. And then our bottom is actually going to be our hot surface, so it's very close to boiling. So this field, rho GH, or pressure minus rho GH, is a little bit complicated, but essentially what it is your pressure minus the effects of rho GH, so, or the hydrostatic head. And so what we're doing is we're setting the internal field at 1 atm. That's just pretty standard, unless you're doing, a pressurized reactor of some sort. And then the typical wall boundary condition is fixed flux pressure. That's based off of the internal field here, or what's calculated. And then your front and back is going to be empty, and then usually it's a safe bet to place the utmost top face, if you have gravity going downwards, as the fixed value. Now it doesn't always work, and sometimes you have to go into the solutions and specify what cell is as a reference for that rho GH. And because we have that, we just leave everything in the conventional pressure term as calculated, because everything will be calculated in this field. All right, we are ready to run our simulation, but before we do, let's make the block mesh real quick and look at the mesh. So how I visualize things is using pair view. Pair view is very useful, and you can see it's been developed by Los Alamos and Sandia, as well as a few other companies. And so how you actually look and visualize that OpenFOAM files is you go into System, and you always select Control Dictionary, and then you scroll down and find OpenFOAM Reader. Apply. So here's what our mesh looks like. It's a very simple mesh. It's going to run really well because there's no curves, there's no non-orthogonality. It's just a block with lots of little cubes. and you can see it's two dimensionals, and yeah, it's a very simple mesh. All right. So I'm going to start by decomposing everything, and as you can see, put it into different folders for each processor. And this is basically a function which runs in parallel, and I have 8 number of processors is what that stands for. And then the solver I'm using is OpenFOAM, and I'm going to run it in parallel. So what this is doing is now it is stepping through the solver, and it's giving us residuals, and it's actually best practice to plot those, but for this very, very simple simulation, I'm just not going to. They're a little rough, but there's usually a threshold which means that they are converging. So we'll let that run. All right, our simulation is finished. As you can see, each time step it gives us the coordinate number mean and the max. You never really want the max to go over 1, or you get kind of non-physical results, and they'll often crash a heat transfer simulation. That's your delta T for each step, and then there's your time, along with those residuals, which are very useful for looking at the convergence. So once you're done with a parallel run, you have to reconstruct all the fields. As you can see, it's reconstructing and then making a folder for each time step. Normally you wouldn't record this many time steps unless you had a lot of storage. But because this mesh is also very small, there's probably not too much memory here. Let's see. Yeah, it's not that bad. Sometimes there are time steps which are, several gigabytes each time step. All right, we've reconstructed the case. Now we're going to open it up in pair view. If you've already pulled it up once, you can just go to your recent files. So we're going to start with the temperature, and this is like the very first time step that we're looking at, and you can see that our bottom is pretty hot there. So you can apply different color schemes to kind of get a better idea what's going on. It's a pretty good one when you have a hot cold zone, and you can actually export all these time steps as an animation, but it's fast enough that it's running at animation speed here. And how you do that is actually just going to your export animation scene, and there's a few things that you can set up. Let's see, I'll take time. So there's our time, and you can always change the text, make it bigger, bold it, because our mesh is a little coarse, it's not going to capture everything. It's not a direct numerical simulation, but it's pretty close because it is very slow flow and it's laminar. So you can kind of see the growth of the boundary layer right there. But it's not terribly interesting. This isn't a very exciting case, but it's a very basic one. So that's our temperature field. And if you want to change this, drag that there, and then you can make it a little bit more visible. There we go. So we have, the bulk of everything being ice water, and then that very small surface being a little bit warmer. So there's a few ways you can extract data, and it's quite lazy to do it from Pair View. There's better ways to do it in OpenFOAM. So the first one is plot over a line, and we kind of want to set it up in the middle of our simulation here. Let's see what that looks like. And we want to filter out velocity and our pressure minus rho GH, and that gives us a temperature profile there. So that is how you run a very, very basic OpenFOAM simulation.